Hello everyone again and welcome to the DMSI YouTube channel, and it's truly a pleasure to actually have you all in this particular space. And in this particular video we're going to be exploring and following up from where we stopped on our previous video, which involves the idea of flux. And from our idea of flux we are connecting two properties. One property is the main property, and while the other property is a different one, but in this particular case we are doing the derivative or the first derivative of the other or another property. So in this particular video we are associating two properties in terms of how they are moving, or the mobility state, at a specific rate, and this rate of mobility is going to be done with respect to the area and also at a specific time period. So on our previous video we looked at one, how are we going to associate this property which involves matter, and in this case here we know that the matter flux is connected really well to the specific property, which is another one, which is called the number of particles. And the number of particles will be distributed over a specific area at a particular time, and that mobility is actually where we linked our relationship between the transport system and where it is coming from, where on one side we have the property, which is in this case diffusion, and diffusion is going to be depending on the transport property, which is called, or transport quantity, which is called matter or our particles. So in this part we were able to determine our D, which is represented as the diffusion constant, and this diffusion DC constant is actually equal to 1 over 3 multiplied by lambda. Lambda in this case is expressed as the mean free path, and this is multiplied by our mean speed, and the unit for this was considered to be meters squared times second to the power of -1, so which is per second. So this was what we talked about on our previous video concerning matter flux, and on our video today we're going to be looking at another type of flux, which is considered to be called, in this case, energy. And the energy flux means that you're looking at energy that is transferred by a particular medium from one specific part to another at a specific area at a specific time period. And so the energy flux, which is expressed as J, and J, which is our representation for flux in terms, in this case, of energy, we need to be able to address a specific system first, and from there we're going to make conclusions based on this particular system. So if you have a specific container or material that contains various particles, we have our particles that are going from high temperatures in this particular region to a much lower temperature. And so what is happening here is that in this case we are going from a specific increase in the flux, where we have our energy of the flux to be positive values, which means it's greater than 0. So since we have this, how about we have our relationship between our z-axis and the temperature, which is represented as the y-axis. And what we notice is that there is a curve that steeps down, and this, by doing the derivative in this case of each specific point on this curve, shows that we have negative values of our slope, which means that our slope of the temperature, in this case it is the first derivative of our temperature, or we call it the temperature gradient, is less than 0. So therefore we notice that as we move from left to right, we see that we're going from bigger negative values to much smaller negative values at increasing energies. So therefore we can come to the conclusion that our energy flux, take note, energy flux increases as the first derivative of our temperature increases. So therefore our first derivative is directly proportional to the energy flux, and so therefore we can then build on this relationship of our relationship with the temperature gradient and the energy flux by introducing a constant. And so since you know, take note of this, since you know that our energy flux, which is a positive value, which means that based on this here it is greater than 0, we also know that our specific temperature gradient, which is expressed as d at t over d at z, is a negative value. So since you note this, we can then create our constant to be a negative value so that our right side will be equal to our left side in terms of the signs. And so therefore our constant that we're going to be introduced is represented as k, and k is going to be a negative value. So therefore our final expression for our energy flux that connects our energy to the temperature is going to have our k value, which is a negative value, and it is multiplied by the temperature gradient. And so in this part we can then lead to the conclusion that our k is noted to be not the Boltzmann constant, but indeed the coefficient of our terminal thermal conductivity. And so this is linked to the gas molecules, that is a perfect gas, as they carry energy as they move from hot regions to cooler regions. So this coefficient of thermal conductivity will be addressed when we show our coefficient, which is represented as k, to be equal to this particular relationship where 1/3 of our specific mean free path is also multiplied by our mean speed, and this is also multiplied by our molar, take note, heat capacity of our gas at a specific volume and or at a constant volume, and this is multiplied by the concentration of our specific gas, which is the molar concentration of our gas, which is in this case going to be represented as A in the brackets. So this is one way to address this particular formula, and the other way comes from what we know about our specific mean free path, where our mean free path is equal to kt, which in this case our k here, not this big k that we have here. This small k is the Boltzmann's constant, and this is all divided by our specific pressure multiplied by our specific cross section of the molecule or particle, and this is multiplied by our square root of 2. Take note that also for this other variable, which is the specific mean speed, our mean speed is expressed as the square root of 8 multiplied by our specific k, which is the Boltzmann constant at a specific temperature, or divided by the pi of our, in this case, mass of the specific atom. And on the other side, this is also equal to the square root of 8 multiplied by r, which is our gas constant, times T, temperature, or divided by the pi multiplied by our molar mass of our specific particle. So once you introduce these two expressions into this equation, we're going to be able to arrive at our new k, or related k, which is our specific coefficient of thermal conductivity, to be equal to the mean speed multiplied by our molar specific heat capacity of our gas at a constant volume, to be all divided by 3 multiplied by the square root of 2, and this is multiplied by our specific cross section of our gas molecule at that number of particles. So these are the two equations that connects really well to our specific thermal conductivity coefficient, and this will be important in here because it highly shows various interesting interpretations of our outcomes. So interpretation time includes the following. First is that we note that at a particular mean free path, when this increases, we have our pressure to decrease as shown in this particular relationship here between our lambda and our specific pressure. So therefore, this inverse relationship between our lambda, which is the mean free path, and that of our pressure also shows that it is as well inversely proportional to our specific concentration of our particles. Therefore, this highly leads us to come to the conclusion that Rk, which is the thermal conductivity coefficient, is independent of our specific pressure at very high pressures. So at very high pressure, you actually have this particular independence, not really that this particular independent relationship with Rk to be established. So what is the implication of this? Why is this the case? When we have increase in Rk, which is the coefficient of thermal conductivity, this leads to relationship with more particles, so an increase in particles that will transport energy. And so once you have more particles that are transporting a specific energy or more energies, our specific decrease in the lambda, which is a mean free path, is leading our therefore energy to not be carried over long distance. So therefore, in this case, this prevents our pressure to directly connect to our K value, where our K value is very high or our pressure is very high in this particular case right here. However, on the other side, for our pressure, which is on the opposite side, we have a situation where we have a low pressure. It means that our K would be directly proportional to our pressure. Therefore, this at very low pressures will be satisfied. And as a result of that, once we have low pressures being satisfying to this particular relationship between our pressure and the coefficient of our thermal conductivity, we notice that in this case, our lambda, which we expressed initially here, is going to be going beyond the dimensions. So therefore, once it goes beyond the dimension of that specific system or space where the particles are in, this results in the transport of energy to be established at a specific distance that requires the same size. Therefore, energy will be pushed in this particular system or favored in this particular same size of this container, that later results and also limits the particles size from influencing this particular system right here. So therefore, energy is facilitated, which is not dependent on the size of the particles. Therefore, in this case, we have our specific energy flux to be highly dependent on the specific lambda, and therefore we have our specific thermal conductivity in terms of the coefficient to be not only directly proportional to the concentration of our particles in this space right here, but also the specific coefficient to be directly proportional to the pressure. Take note that this has to be done at very low pressures. So that is the first particular interpretation of this particular expression that we have right here. And the other interpretation that you need to keep in mind is that we have our specific K value to be increasing as the gas with a specific heat capacity increases. Therefore, this is noticed when you have this done at a constant volume, and it is shown in not only this particular expression here, but also in this particular expression right there. So therefore, in this case, this is due to a given specific temperature gradient that results in an increase in the energy gradient of this particular system. And so this is going to be important in terms of our understanding of how temperature and energy highly relates when you have a specific K value to increase as a result of gas molecules specific heat capacity to increase. So that's about it for our understanding of the K value, which is the specific conductivity thermally of that particular gas in terms of its constant, with other variables that we've experienced not only in terms of the mean free path, which is the distance between particles before they collide, and also looking at the mean speed, that is where speed of particles plays a huge role in overall distribution of energy from one path to the other, and how this is important in not only understanding how flux means, but also how energy flux is highly connected to energy, just as we have diffusion connected to matter. And so therefore, in terms of looking at the property of focus, we have our specific thermal conductivity to be the property conductivity to be the property, and why we have the transporting quantity to be, in this case, the energy, as our diffusion is the property and the transporting quantity is indeed the matter. So that's about it for this particular video. Hope you're able to understand this. Please hit the comment down below. Let me hear your thoughts about this, and take note that in here our specific unit for joules is measured in energy flux is measured in joules, and this is per meter squared seconds. So that's about it for this particular video. Hope to see you on the next one. Next video, we're going to talk about interesting things involving the examples and how to derive not only this unit, but also deriving the K value, or the coefficient of thermal conductivity unit, which is represented as, in this case, we have joules per kelvins to the power of -1 per meter per second. So see you on the next video. All the same, stay smart as always, and believe in yourselves.